And let me go to the whiteboard here. Yeah, so today I'm just going to talk about, I was going to talk about CNNs, but, you know, I kind of anticipated that it was too short a period of time for that. So instead, I'll probably just move CNNs to after spring break. And instead, given that you guys worked on the ethics homework, and that was mostly NLP, and you were using transformers, I kind of decided that I was just gonna, for this week and next week, I'm basically just gonna talk about transformers instead. Okay, so we're just gonna do that. That should be pretty interesting. And then we'll come back to the rest of fast AI, for instance. So all of this is still Python. It's still, PyTorch, the focus. Just remember, we are using these two frameworks. In particular, we are using fast AI for many types of problems, vision-based and tabular, basically. But as it comes to NLP problems, natural language processing, kind of the state of the art right now, or at least a lot of the excitement, is with transformers. And as you've been using, with this company in particular, Hugging Face, which they didn't invent transformers, but they've created that Python library, transformers, which allows you to do a lot of things, right? So that's really what I'm going to talk about a little bit today, just getting into the motivation of how transformers work. Okay. So let's start kind of with the high overview of transformers. So let me just make sure I'm recording. Yeah. All right, so transformers actually, so let's kind of talk about it. So let's talk basically of where they come from. Really today is more like the history and everything. So as you guys know, in 2012, it's really when like deep learning started. And then sometime around 2014 or so, they developed a technique called Rnns with something called the Lstm. Okay. And the RNN, the Lstm, basically it's a sequential model. So when you have in machine learning, in deep learning, when you have, the cat is sleeping on the, and then blank, right? So that's kind of the problem that you've looked at with those masks. So in the past, this type of a sentence would be, you would think of it as being a sequence basically, right? So you would go from the to cat to is to sleeping, then to on the, and then you would predict this. And this was usually referred to as a sequential machine learning, sequential model. So they develop a technique called Rnns, which are called recurrent neural networks. It's never been one of my favorite deep learning algorithms, actually. I always found it difficult to understand and difficult to model. The results were okay. They were the state of the art, I should say, in NLP at the time. But they suffered from several problems, and that's really kind of the telling you the story of transformers, basically. So so now you have these techniques where you have inputs, sequence of inputs, but it's sequential, the inputs, and you want to create a neural net. So imagine this is the hidden layer. So the inputs go in here, kind of like that, in the recurrent neural network. and then they would come out as outputs. Right? Come out as outputs here. So we can say these are the outputs, and these are the inputs, and these are the hidden layers because they're neural nets, right? Like that. And then you would create this model, and this is a sequence. So this is a sequence. So for instance, text, the cat is sleeping, something like that. And then the recurrence is because we know that the goes before cat, cat goes before is, and so on. So that we have to capture this idea of the previous state. So what would happen is the input goes in, but then the hidden state would go into the next hidden state like that. And then you have a new input, but the combination of these hidden states go in. And so now you have this idea. And then this here, these can actually be several layers in a deep learning algorithm. So it doesn't actually just have to be one, it could be several, okay? And so these were basically the models. And then sometimes you would predict things. So for instance, in the classic example of name entity recognition, you would say, for instance, this is not an entity, oh, the cat is. So the cat should be marked as an entity. This is not an entity, and so on, right? So they are sequential models because of that. Or sometimes you can have a sequence of things and you predict some class, right? And the class can also go here. So you basically train a model and try to learn a class. So this was the issue. However, if you think about it, what's happening is, if you remember in machine learning, you're multiplying things, right? So usually the equation in machine learning is W times X plus B, right? And that could be this is the X, right? And then these are the W's, and then you get that hidden state. But then this is hidden state, let's say 0, right? And now to get hidden state 1, well, it's gonna be what? Hidden state 1 is, and then this, let's say that, and this is W1. So now this is going to be H0 W1 plus B. So you see, you now multiply H0 times W1, and then you just keep doing that, right? So this could be hidden 2 with its weights 2. So if you want hidden 2, that's going to be hidden 1 times W2 plus B, and so on. So you have this multiplication, right, over time of the weights, multiplying in a sequence that's very long. So what can happen, inside here, you also have other hidden layers possibly, right? And so what can happen is there's a classic problem in Rnns called the vanishing gradients problem. And what that means is basically, think about this problem. If I multiply 0.1 times 0.1, what does that give me? It's like 0.001, something like that. And now if I take this and multiply it by another tiny number, the numbers just keep getting smaller and smaller and smaller until basically they might as well be 0. So what would happen with Rnns is that sometimes you would have this problem that is called the vanishing gradient. So the weights at the end would become very tiny and almost meaningless, basically. They weren't really doing anything, right? And so that was the first problem. The other problem is that the system is recurrent, right? And it's sequential. So that means this now CPUs, you have CPUs and GPUs. So CPUs are very good for sequence, but they're terrible for parallel. Whereas GPUs are very good for parallel, okay? So the problem with Rnns in a GPU is that you cannot really parallelize them very well because you have to wait, you have to wait for this to process before you can process this one. And then once this processes, you can go to this one, then that one, then that one, then that one. But they don't parallelize very well, okay? So those two problems, the vanishing gradients, which I wrote over here, and the fact that it doesn't parallelize well for GPUs created basically a weakness for Rnns. Okay, so Rnns were not very effective because of that. And so around 2017, a paper came out by Vaswani et al. And the paper is called "Attention is All You Need." And this paper that, think of it, as only came out in 2017, and in December of 2018, right, when the world basically started to learn about it, it's called "Attention is All You Need," but it's actually, it talks about, it first introduced the complete architecture of the transformer model. Okay, the transformer model. And the transformer model deals with the problems of vanishing gradients, and it deals with the problem of the fact that you can't parallelize well the data. Okay, so you no longer have an architecture like this. You no longer needed recurrence. You can give inputs to the machine, but that you didn't have to wait for the previous states of it. Okay, and so that's really, those are the two innovations that made transformers really good. Okay, so transformers after that became extremely important for NLP applications. Its first application was for language translation. So that's usually when people want to talk to you about transformers, they always ask you that question. Do you know what vanishing gradients is, right? They always want to, like, basically want you to tell the story, I guess. So so that's one of the ideas. And then they also parallelize really well. So transformers were first used for language translation. Okay, that was the first use. So that basically means, you have the cat sleeps, which translates to el gato duerme, right? So you have this, and that's what you want to happen. You want the architecture to take in an English sentence and give you the Spanish sentence or the other language sentence. And that was actually the original discussion of it. So way before, so you guys, in the course, we have looked at Bert, Albert, Alberta, I think, Roberta, and so on, right? We've looked at those transformer models, but all of those actually come from this one, from the transformer. The original transformer actually had a very long name, right? So had a very long name. So we'll take a look here. And so I would recommend, if you guys have time, to just get this paper and read through it. Attention is all you need. It's a pretty good paper. I also wrote a description of transformers that I'll probably share. Keep in mind, as I said, transformers is the most complicated deep learning algorithm. It is definitely the deepest. I mean, this is deep and complex. I'll talk a little bit about that today. But the description that I wrote of transformers and the code is like 100 pages long. So I'll share it with you guys, but it is definitely a tough one. Okay, so that's why it's so difficult, in fact, that most people just kind of gave up when writing the code from scratch. And this is why we have this thing, transformers, and then we have transfer learning, and we have pre-trained models, right? Because first of all, even if you build a transformer, they only, you know, the way to gain the advantages of transformers is that you have to train them on massive amounts of data. And usually it's only like the Googles, the Facebooks that have those massive amounts of data. Someone asked me the other day, are transformers really that much better than Rnns? Right? Because Rnns was, you know, state of the art in NLP, as I explained. But now transformers are all the rage. So somebody asked me, is it just hype or is it a reality? You know, is it really that much better? And I guess my answer would be that Rnns, that they probably are, that transformers are better because of one simple thing. Because they don't have this issue with the vanishing gradients, or it's reduced, and because you don't need to process every, you know, one thing and then the next in the sequence, but you can process things in parallel. You can process them in GPUs. So that means that you can process more data faster with them. And so I think that's really the advantage of transformers, right? So they have some nice architectures. They have some nice little tricks, like something called the attention mechanism, which is really interesting. But at the end of the day, I think the main advantage of transformers is that even if Rnns are good, they cannot process the amount of data that a transformer can process, not in the amount of time that a transformer can. And so that's really where the advantage comes in. Transformers, you know, versions like GPT-3 and, you know, all those, you know, versions of transformer have been trained on like millions and millions of records, right, of text. And so at the end of the day, I would think, my opinion would be that they are great. It's not so much, if Rnns, I guess my point would be, if Rnns could be parallelized, just like transformers, and they could process as much data at the same speed, they would probably be comparable. But I think the thing that kind of killed Rnns is this idea that the transformer is, you know, very fast. Okay, so I kind of wanted to motivate that because, you know, a lot of people will say things like, you know, is it hype or not? But, you know, I don't think it is. All right, so that's one thing. The other thing is, obviously, we don't all have the amounts of data that Google has, right? You know, I actually built a transformer from scratch. I was able to get a data set that had 2 million pairs of sentences. I got pretty good results with a GPU box. I think it took me like 24 hours to train that model, but that's nowhere near what Google can do. And one thing that transformers have shown is that the more data you give them, the more they can learn, the more they can infer about the world. So then that's where that new model has come in of Hugging Face, right? CO, where they have embraced the idea of transfer learning. And so now they basically have this hub where you can train a model, you know, or you can use pre-trained models from Google, et cetera, fine-tune them, right? Fine-tune them, and then adapt them to your problem. Okay, so that will be one of the things that we will do, you know, in the semester, right? So far, what you've done in the lab in your assignments is you basically just used BERT, which was one of the original transformers. There's also GPT-3 now. This is the state of the art currently. And then there's Roberta and all of those. And you guys have used these with the, you know, kind of the plain vanilla pre-trained model, but you haven't really fine-tuned the model, right, to your own problem. So that will be one of the things that we have to do later in the semester, okay? But anyway, Hugging Face has developed this model where you can, from the hub, download pre-trained models and then use them for your specific problems. Okay, and I think you'll see that BERT is in particular, BERT and BERT variants are the very the most popular ones. However, the very first implementation, the 2017 implementation of transformers, is actually called the encoder decoder with multi-head attention. So that's kind of a long name, but that was the original one. And it basically captures the architecture of the original transformer, which was, as I said, for language translation. Okay, so before I continue, are there any questions about this? Guys, are you following along?
No questions.
So let's think a little bit about, so what I'm going to do is I'm going to do a diagram of this one, right? So we're going to start with the original one, the encoder decoder with multi-head attention, which was used, as I said, for the language translation problem. Later in the semester, we're going to start looking at variants of, like BERT and the other ones and how they work. But just be aware that they all pretty much come from the same original code, okay? As I said, for this algorithm transformers is really complex. So I'm going to keep it at a very high level. We're not going to implement this from scratch by any means. And so instead, our approach will just be to use the pre-built, pre-trained models. But we will fine tune. That's definitely one of our goals. And then we'll explore the applications beyond language translation. So probably the best thing that we can do is to understand this is to look at a high level of what a transformer is. So a transformer is actually just a lot of these. That's it. Transformers have a lot of those. They have some additional mechanisms within those mappings, like within, more mappings. In between, there might be something called an attention layer, right? There are residual layers as well. But if you remember, these are the basic standard, are kind of feed forward, right? The mechanism that where we build feed forward, layers basically. So it's really just this. It's a whole bunch of transformations, and that's where the name really comes from, okay? So transformers, basically, when you think about them, you have to think about them in terms of whether you are training or testing. So you may be training or you may be testing, right? So it's the same architecture, but the inputs and the way that you train varies a little bit, okay? So we kind of have to think, well, if we're training, the logic is like this. If we're testing, the logic is going to be like this, okay? So that's really the only thing to consider right now. All right, so usually then, the first thing that you do when you talk about transformers is you look at the architecture of it. All right, so we're gonna look at it at a very high level because this is very involved. We kind of have to see it, almost like boxes of how it works. But let's take a look at the transformer architecture when you're doing training only, okay? So during the training, okay, you have basically an architecture that should look like this. So you have input, and this is very high level, okay? You have input, then you have a big thing that is called the encoder. So you give it the input, it goes into the encoder, and you get what is called the encoder output. Okay? Then on the other side, you have what is called the decoder. And if it helps you, if you've ever thought about like compression or those kinds of algorithms, like zipping a file or whatever, there's similarities to that. You encode and you decode, okay? So you take an input, which is, by the way, this is a tensor, right? You guys already know what a tensor is probably a matrix of several dimensions. And guess what you get over here? You get another tensor, which is probably a matrix of several dimensions. So let me actually write this in another color. So this is a tensor. And am I recording this? Yeah. Okay. So this is, as I said, a tensor. And then now we go back to the colors. We have the decoder, and the decoder will have, and by the way, this is the original 2017 Vaswani paper, okay? So that's the one I'm describing, the original one, given that there are other variants, but they're gonna be different, but based on the same idea. In the decoder part, you have another input. But in this case, this is input A, this is input B. So they are actually not the same input, okay? That input goes into the decoder. Another parameter that goes into the decoder is the encoder output. So basically the input goes to an encoder, the encoder output comes out, and then this feeds into the decoder with input B. And then over here, you now have what you're trying to predict, okay? Which in this case is another tensor. And this is a tensor. Now this is where it gets a little bit tricky, okay? Because it's trying to predict something depending on the problem that you're looking at, okay? Depending on the problem that you're looking at. It's trying to predict something. So this is basically for training here. Okay, but usually it'll be this will usually be, it's trying to predict some kind of a tensor that represents what the problem is. Okay, so for instance, a word, or it could be a sequence of words. Okay, all represented by tensors. So this is actually a very high level overview of the transformer. However, to understand it further, we have to dig in, or zoom in, if you will, deeper into this. So let's take an example of, let's change to another color. Let's take the example, the classic example in the Vaswani paper is translating English to Portuguese sentences, right? So that's what it's trying to do. So here we have, in this one, we have the English sentence. That's the input. The English sentence then goes through a whole bunch of transformations, and then it is encoded into a specific vector of a specific size that you can define. You define what the size of the dimensions of the tensor are. And then that encoding, which is sometimes called the context, becomes an input to the decoder over here. So this is the encoded English sentence, okay? Then over here, you have, in the decoder side, the input is going to be what? It's going to be the Portuguese sentence. So the Portuguese sentence becomes the input to it. So you might say that's kind of funny because you probably expected the Portuguese sentence to be over here, right? That's kind of what you expected. And you would be correct. The decoder also has the Portuguese sentence as well. Like that. Except that it's the same Portuguese sentence, but the Portuguese sentences are shifted. That's the only thing. So you have an English sentence here. This is the encoded English sentence. This is the Portuguese sentence, which gives it the encoder here. And then it produces another Portuguese sentence over here. Now, what's important about this is, believe it or not, the only thing that it cares about is the last word in that Portuguese sentence. That's what it's trying to predict. So it predicts sequentially, right? So for instance, the input might be the cat the cat is sleeping, right? And so that's going to be, I'm going to use Spanish so that, you know, I don't know Portuguese. So gato. But here you have this, right? So that's the translation, literally. However, you want the model to learn, right? So you want it to learn, let's say, this word, right? So what you do is you shift the two Portuguese sentences, this one and that one. So that would mean that you would have that sentence twice. So this one is the input in English. And then this, now you have, so this, like that. And then blank there, right? You don't have that word. Or because they are shifted, actually, this would be, there's a special symbol for beginning of sentence. So I forget what the code is, but let's say, the code should be, start of sentence, yeah, so SOS. So you have these special symbols that indicate start of sentence, end of sentence, whenever you're training your model. So you actually then, when you do this, it's gotta be like this. Okay? And the other sentence is shifted, so it would be, do you guys see that? And so what the model is going to do, if we just focus on this part here, is that you would feed this part here and that part there. You see that? So that the model is always going to learn the sequence, because it learns, okay, I learned the English sentence, the whole thing, right? Because in a translation problem, you know, you'd have the English sentence, you want to translate to the Portuguese sentence, but you also know that you've already said a few words of the sentence because you're predicting one word at a time. So basically that's what's captured with this little trick, which might seem confusing, but this is how it's done. You have start a sentence, these words, and then this is shifted by one word. And basically, because you know the English sentence and you know where you are in here, the Portuguese sentence, now it's going to learn that the next word is that one because this one goes over here. And that's exactly how it learns. Okay, so usually when you read the description of how transformers work, they just basically say, well, you give it the English sentence, the Portuguese sentence, masked by some words, and then it's just going to predict that word. Well, yeah, it predicts that word, but when you're training, you actually give it the shifted words in the sentences. Do you guys understand this idea?
I think so.
I think so. Okay, yeah. So that's basically the concept. Okay, that how you do the training. Now you don't put, like, you don't black out words or anything like that. Instead, what you do is, like, if I think of this one. And then the other one, start a sentence. See, the sentences actually do have all the information. They haven't been, because this one will just be end of sentence. They haven't really, you don't have to take out the words or blank them out or anything. The words are there. Instead, what you use is something called the mask. You probably, if you were reading through the code, you saw a lot of that, these masks, right? And what these masks do is they're basically, you multiply this times a vector of zeros and ones. You see that? So you multiply these times these vectors. And so what this does is it basically tells you what to hide by multiplying times this mask. So for instance, I have here, let's see, I have, so I would not have that and that. And I want to predict this one in the given sentence. So then you would have to mask this as, oh, sorry, you have to mask this as one, 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 and then these are zeros, you see? So it's basically a little trick that you do. Every sentence that you send it needs to have a mask that indicates which characters should be ignored by the algorithm and which characters should not be ignored by the algorithm. And that's how you control this whole idea of hiding some of the words, okay? But at the end of the day, that's really the basic logic of this, okay? That you have this architecture like that, okay? So that's the very high level architecture. And then, so the sentences are shifting when you're training. When you're testing, when you're now testing or predicting, you still have, right? You still have, the input, right? This is the encoder. This is the encoded input, basically. So the encoder or encoder output, let's call it. This still goes into the decoder. Still goes into the decoder. Here you still give it, this will be like the English sentence. Here's the Portuguese sentence as an input. But here in the prediction, now you don't have the sentences, right? So obviously this would be, you're predicting a new example. You're only given the English. So what do you do then? Because there's actually no Portuguese sentence. So what happens is you only give it start of sentence. You see that? Because it's kind of, this was actually worked in, if you remember, into the training, right? That you started with start of sentence. So when you train, you give it full sentences, the full Portuguese sentence on the input and the output of the decoder, but shifted by one. Shifted by one. And then you use that masking mechanism that I talked about to kind of hide the words, because the words are there, you just hide them based on the thing that you're trying to predict. That's how you train it, because you want to do it like this because this is correct, right? You know, exactly when you give it the Portuguese sentence, the original just shifted, you know it's correct. That's like the training set. In the test set, you don't have the sentence, right? And so all you give it is start of sentence here, the symbol. You give it the input, which would be, the cat, everything, and then it's going to predict that, right? The first sentence. So then that sentence kind of becomes, it increases the input. And now the next output would be what? Cat, right? In Spanish, you got, right? And then that word gets added to the input. And so now you do the next iteration. You see that? And it predicts that, and it plugs it in. And then it's going to say, okay, what's the next one? Okay, I predicted that. It adds it. Okay, what's it gonna do now? Well, the input was the cat was sleeping. So then it just says, that's the ending symbol. So it plugs the ending symbol to it, and that's it. The algorithm stops at that point. Do you guys see that? So that's how it does the testing. It's basically, or the prediction or testing, it's predicting one word at a time and then adding it to the input. However, you cannot train like this. You can only, it makes sense to test like this because, let's say you're now in the wild and using the translator. You don't know what a person's going to say in English, right? So you don't have the translation. It needs to do the translation. So testing wise, it works like this. But training wise, we have to do that little trick of we provide the Portuguese sentence both here and here, just that one is shifted so that we have the sequence of words and then we just predict the last one. And then we don't actually delete the words or anything. We just mask them by multiplying them times these vectors. Now, who can tell me, why do you think, because I think the testing is pretty intuitive, right? This should be pretty intuitive. You give it an English sentence all at once. It does some whatever this is, but you have an encoded tensor, feeds it into the decoder, and then here you just start with the start a sentence symbol, do all the things, predicts one word at a time, pieces it together until you get to end of sentence. So you guys get this one, I think, should get this one better than the training part, correct or no? Guys? Mm-hmm.
Yeah, it makes more sense.
It makes more sense. So the question I would say is, why do you think we can't train like this? Why can't we just train like this? Why do we have to do that thing where I have two sentences and I shift one and, why not just do it like this? Give it some training data, and what do you think the problem might be? If we train like this, would you agree that, especially when it's first learning, that it would make a lot of mistakes? Would you agree that the model would predict bad things, especially when it's first learning?
Yeah.
Yes. And so what would happen? It's predicting bad words for the sequence, and then it's using those bad words in the sequence to predict more words. And it becomes this infinite thing of predicting bad things and learning bad things. You see that? And so the model would have actually really bad performance. And that thing was a challenge that people had for many years. They couldn't figure out, man, because this is actually intuitive, I think, if you think about it. But they couldn't, they found that was not very good. And so what they came up with is that during training, as I said, they said, let's not even consider using bad data. Instead, we give it the Portuguese sentence, we shift it by one, so that if we give start a sentence L, you can see it's the same thing, right? It predicts one word, then the next and the next, because the masking works like that. You start with the beginning and then you start removing elements from the mask until you get to end of sentence. This is called teacher forcing. So this has a name, and it's called teacher forcing. And this technique was applied. This is just one of many techniques that had to be applied to transformers in order for them to learn really well. So now whenever when the first paper came out, the Vaswani one, for the decoder encoder with multi-head attention, it actually did this, right? So it gave it the English sentence, the Portuguese sentence, and the Portuguese sentence shifted by one on the other end, and then it just learned the mapping so that it was always correct. Okay, this is the training set. But the architecture is built in such a way that really at this level here, it's only predicting one word, the next word. Always, always just predicting one word, given wherever you are, whether you're at standard start of sentence or in the middle of the sentence or wherever, it's always just predicting that word, because that way, when we go to the testing phase, it just works perfectly and we don't have to modify anything. We're kind of doing the same thing. You know, it's predicting one word and then it's building whatever word is predicted, it gets added to the input again until it gets to the very end. Okay? Questions about that? That's in a very overall, that's how it works. If we just think about inputs and outputs, that's how transformers work. And again, as I said, this is only for the language translation problem, but from there, then people came up with other applications like named entity recognition, part of speech tagging, summarization, sentiment analysis, classification in general, and so on. Questions? Okay, not hearing any questions. All right, so then I did this from a very high level, right? Just the inputs and the outputs. So now you might ask yourself, what is in these encoders and decoders, right? Because I said, you know, there's an input, there's the encoder output, and then there's this encoder itself. So what is in it? Right, and then the decoder, you know, what is in that? So you have input and the prediction, right? So let's say predicted vector. So this is basically a whole bunch of transformations, a whole bunch of y equal w x plus b, a lot of those. In fact, the encoder has, the original Vaswani paper had 6 what are called encoder layers. 1, 2, 3, 4, 5, 6. So it had 6 encoder layers. They're exactly the same. They all are exactly the same. And then the decoder, this is the encoder, this is the decoder, also had 6 what are called decoder layers. They're exactly the same except for the last one. 1, 2, 3, 4, 5, 6. There's one normal feed forward, you know, standard like deep learning layer, because it's the one that kind of maps to the predicted vector, which is usually the size of the vocabulary. So this will be size of vocabulary. You guys see that? And so these encoder layers are basically, you know, you have to kind of zoom in now and look at what it is that they do inside. Okay, so you have to zoom in basically. And what they have is they have 2 layers each, 2 layers each, where one layer is just this standard thing, the, you know, our basic feed forward connected layer, but they also have a thing called the attention layer. Okay, the attention layer. All right, and that's a new thing. So this, you know what it is. So there's a whole bunch of these, right? So it's just like a neural network where, you know, in a neural network, this is hidden 1, hidden 2, hidden 3, hidden 4. You're all familiar with that, right? And you understand that. But every encoder layer has those, plus it also has this thing called the attention layer. And the attention layer is actually not a new concept, but a specific concept that's important for this, okay? That we will have to talk about. Now, I think we can stop here because this is a good stopping point. So in the next lecture next week, we will pick up on the attention layer and just kind of get a feel for how that works. Make sense, guys?
Sounds good.
Right, yeah. So as I said, one other thing that I will do is I will give you a PDF of something I wrote on transformers. So you'll read that. I also recommend you read the Vaswani paper, 2017. I'll provide that one as well. So definitely, guys, transformers is something that will take a long time to study and learn. And we'll cover it and discuss it in the lecture. You'll do the reading. But at the end of the day, you're not going to implement it from scratch, and we're only going to use it through the Hugging phase framework. Okay? So that's kind of, so hopefully I'll have an example of fine tuning next week, and we'll continue the lecture on transformers next week. But we'll stop here, given that you guys will be starting your exam at 3:30. So let me go ahead and stop the recording.